Okay, I want you to picture this. You're standing out on the deck of an offshore platform, right in the middle of the Gulf of Mexico. It's 2 a.m., the air temperature is a stifling 35 degrees Celsius, and the humidity, yeah, that's sitting at a solid 100%. It's thick. And through that heavy night air, you can actually feel the steel deck vibrating right beneath your boots. What you are feeling is a sleeping giant waking up, a massive gas turbine generator spinning up to 3,000 RPM. Welcome to The Explainer. I am absolutely thrilled to take you on this journey today into the real heart of offshore engineering. We're going to break down exactly how these incredible, massive machines work, and, more importantly, we're going to walk through the completely gripping step-by-step sequence required to awaken them without accidentally triggering a total platform blackout. It's this wild mix of raw, fiery thermodynamic power and microscopic digital precision. So here's our game plan for today. We'll kick things off with the role of the offshore powerhouse, unpack the basic anatomy of a turbine, and then look at how we govern all that immense power. Then we hit the real climax of this explainer, the rigorous 5-step commissioning sequence. And finally, we'll wrap up by looking at the digital shields that protect the whole thing from catastrophic failure.
All right, let's jump straight into Section 1, the offshore powerhouse, the literal heart of the system.
This turbine isn't just another piece of machinery. Out there on the water, there's no plugging into your local grid. Every single watt of electricity that keeps the platform safe, operational, and habitable, it's produced right here on site by burning wellhead gas. Seriously, if this machine stops, the whole world stops with it.
Moving right along to Section 2, Anatomy of a Turbine, transforming wellhead gas to power. The basic engine runs on what's known as the Joule or Brayton cycle, and it operates in 3 beautifully simple linear steps. Step 1. The turbine aggressively compresses a massive amount of incoming air. Step 2. Fuel gets injected into that high-pressure air and is combusted, creating an intensely hot gas. And Step 3. Those hot gases rapidly expand through the turbine blades, which forces the main shaft to spin. Boom. Power. But here is where pure engineering theory kind of collides with environmental reality. If you look at the manufacturer's nameplate on one of these turbines, its peak performance is officially rated for ideal ISO standard conditions, specifically, an ambient temperature of 15 degrees Celsius at sea level. Now see how heat acts as a hidden thief here? Remember that 35-degree night in the Gulf of Mexico we talked about earlier? Well, for every single degree Celsius, the ambient temperature creeps above that ideal 15 degrees, the physical output of the turbine derates by 0.5 to 0.8%. So that harsh offshore heat is literally robbing the turbine of its mechanical efficiency. You have to push the machine way harder just to get your baseline power. Okay, Section 3, governing the beast through precise control. Brute force is useless without control, right? This control is achieved through a really clever concept called droop governing. Imagine multiple generators running in parallel. If just one of them tries to take all the load, it's going to overheat and fail. Droop governing is a brilliant piece of proportional teamwork. As the electrical load scales up to 100%, the control system intentionally allows a 4% fall in shaft speed, and therefore electrical frequency. This graceful little droop lets the power management system seamlessly share the heavy lifting across multiple generators, so nobody gets overloaded. And that brings us to Section 4, the absolute climax of our explainer, the commissioning sequence. This is a rigorous, highly choreographed 5-step process. Take a look at this vertical roadmap. It's basically a rocket launch sequence for a power plant. We have a strict checklist here, and we're going to watch these boxes get checked off one by one as we travel down the road. Pre-commission, first fire, synchronization, load testing, and finally, protection tests. Every single one of these has to be flawless before we can trust this giant. Ticking off box number 1, pre-commissioning. Before a single drop of fuel is even allowed into the system, engineers meticulously sweep the machine. They run Megger checks to verify the insulation resistance of those massive cables, and they run trip tests to make sure the baseline electrical safety circuits are actually awake and ready to act. Once those baselines are clear, we check the second box, first fire. Oh man, this is always such a tense moment on the deck. It's the supervised ignition of the turbine. They safely initiate combustion and start slowly ramping those incredibly heavy rotors up to a stable, roaring idle speed. The giant is officially awake, it's breathing, and it's stabilizing. Moving down the roadmap to step 3, synchronization. The generator might be spinning, but right now it's completely isolated. Synchronization is the incredibly complex and honestly dangerous moment where this awakens generator finally connects to the live electrical grid of the platform. If you try to close the breaker while it's out of sync, the sheer mechanical and electrical forces will literally rip the machine apart.
To stop that kind of catastrophic failure, the power management system has to nail some insanely tight mathematical margins before automating. Just look at these numbers. The voltage magnitude error must be within a tiny plus or minus 0.15%. Phase angle error strictly between -30 and 0 degrees. And the frequency error is just plus 0.05%. Only when these exact parameters align does the breaker snap shut.
Okay, breaker is closed, we're synced. That checks off box number 4, load testing. We don't just guess that the machine can handle the platform's demands, we make it prove it. Engineers systematically crank up the power draw in demanding increments, 25%, then 50%, 75%, and finally they push this awakened giant to its absolute 100% limit just to verify it's not going to buckle under pressure.
Which brings us to our final checkbox. Step 5, protection tests. We know the turbine makes power, but now we intentionally simulate major faults to see if it can safely and autonomously shut itself down. Checking this last box proves the machine won't just run, it'll actually protect everyone on board when things go sideways.
And that leads us perfectly into Section 5, protecting the generator during daily operations.
Because we really have to ask, what happens when a massive fault does hit? Say a huge compressor motor kicks on unexpectedly, it draws a massive spike of power, and suddenly the grid frequency drops. When the margin for error is as tiny as we just saw, how does the platform survive without just blacking out entirely? The answer is a totally hidden network of rapid response safeguards. We're relying on undervoltage relays, highly sensitive frequency trips, and the brains of the whole operation, the power management system, or PMS. The PMS is basically a digital shield. If a generator trips or a sudden load threatens to drag the whole grid down, the PMS instantly steps in to shed or turn off non-vital loads to save the generators. And this stat right here just brilliantly illustrates the sheer speed we're talking about. The PMS is constantly monitoring the network. When a fault hits, it computes exactly which loads to drop and fires off the tripping signals simultaneously. That entire calculation, plus the mechanical breaker opening, takes just 100 to 175 milliseconds. That is literally less than the blink of an eye to prevent a cascade failure and save the rig from going dark. Unbelievable, right? Like the engineering guidelines tell us, the margin of overload that a gas turbine can tolerate is relatively small. There is this incredibly delicate, continuous dance happening every second, a dance between the fiery thermodynamic power in the combustion chamber and the strict physical limits of the spinning metal blades. And it's all balanced by this stunning digital precision. So, I'll leave you with this. The next time you flip a light switch, whether you're somehow out on an offshore rig or just sitting in your own living room, will you think about that 3,000 RPM giant spinning out there in the dark? Will you consider the heat, the droop governing, and that flawless 5-step roadmap required to weaken it safely? It is a fascinating, invisible world of engineering, and I really hope this explainer sparked a little bit of that curiosity for you today. Keep learning, and I'll catch you on the next one.